This is part 1 of our discussion on kinematics, which is topic 2.1. And kinematics is simply looking at motion, how things move, without worrying about the why behind it, without looking at the forces involved in causing the motion. The things that we're going to look at are speed, velocity, displacement, distance, and acceleration. So let's start with our two most basic terms, distance and displacement. Initially, they seem like they are the same thing, but they're actually very distinct terms when we're talking about them from a physics standpoint. Distance is a scalar quantity. Remember that scalar quantities have only a magnitude and a unit. So for distance, that unit is going to be some distance, some unit of length. So meters, kilometers, millimeters, something of that nature. But it doesn't take into account the direction that the object has moved. It's only the total amount of distance that that object has covered in the time period that it's moving, while displacement is the total displacement. We're using a definition to define it. It's how far it is from its starting position, but it also takes into account the direction. And so displacement is a vector. So here we have how far are you from where you started and in what direction are you. So now it's not only a magnitude, a unit, which again will be a length unit, but it's also going to be a direction from that place of origin. And so to kind of show you what we mean by this, here we have the path that a person may walk. So if the person starts here, and if you've ever seen the Family Circus cartoons where they're running all over the place and it gives you the little dotted track, this is the idea. So our person starts here, follows this very long, expansive path, maybe runs through some trees, there's a forest, I don't know, it doesn't really matter, but they end up at this position at the end. Now the distance that that person traveled is this long, elaborate path that we just traced, but displacement only worries about the start and the finish. So they started here, they finished down here to the bottom right, and so this distance right here, represented by this arrow, is the displacement of the person, the total displacement from the starting point. And then we could either say, we could find an angle here, or we could say southeast. It depends on the scenario that we're given to determine how we express the direction. And so when we have these two quantities, for any motion, the displacement is never going to be greater than the distance. If an object travels in a straight line path from start to finish, the displacement and the distance will be the same. But if there's any deviation from a straight line, then the distance is going to be greater than the displacement. And now this is going to feed into our next two quantities, which are speed and velocity. And similar to our previous two measurements, our distance and displacement, speed and velocity are scalars and vectors also. Then we have speed and velocity. And similar to our previous two measurements, one is a scalar, one is a vector. Speed, if we look at the equation for speed, we see that it's distance over time. Distance we know is scalar. Time is also scalar. And so the speed of an object is a scalar quantity. velocity, on the other hand, is displacement over time. And because displacement is a vector quantity, we have a vector divided by a scalar, the velocity is a vector quantity. And so when we're talking about speed, we're simply talking about how fast an object is covering ground. The units are going to be length over time, so we could have meters per second, kilometers per hour, something like that. But there's no direction. When we're talking about velocity, the units are going to be the exact same, meters per second, kilometers per hour, but now we have to add in a direction to that, so you have to add one extra bit of information for us to accurately be talking about the velocity. Now, these two particular equations are used for two very specific scenarios. The first is if there's a constant, or we'll often refer to as a uniform speed, and that's when the speed stays the same. Okay, so when the speed stays the same, we can use this. We can also use this if we're talking about the average speed. So the average speed over a long period of time. We're going to compare this to what we call the instantaneous speed, but if we're just looking for the average speed over the course of a trip, we can use total distance or total time or total displacement over total time if we're trying to find the average velocity. Okay. We've already addressed this because speed is a scalar divided by a scalar. It's a scalar quantity. Since velocity is a vector, it has to have a direction with it, but both have the same units. Okay? So velocity we can think of as speed with a direction. Okay, so a little bit more about average and instantaneous values. The average is the total change in two quantities, so total change in displacement over total time. That gives us our average velocity. Instantaneous is a measurement at a specific instant. So we get to smaller and smaller fractions of time until we eventually get to an instant, and we're looking at the value or the magnitude of that measurement at that specific point in time. So even if we have a speed that's changing over time, you think about traveling on the interstate, you're not always traveling the speed limit. If there's traffic, you're slowing down, you're speeding up. But over the period of that trip, you might make a 60-mile trip in 1 hour. So your average speed is 60 miles per hour. That doesn't mean that you were going 60 miles an hour the entire time. You might have been traveling at 75 miles an hour at some point if you're a speeder. If there was traffic, you might have slowed down to 40 or 30 or 0. Around here, meters per or miles per hour at one point. So average looks at the whole trip. Instantaneous looks at a specific point in time. Generally, we use position time graphs or velocity time graphs or acceleration time graphs to find those instantaneous values. And then the fifth measurement that we deal with when we're talking about kinematics and looking at kinematics is acceleration. And acceleration is the change in velocity. And so if we kind of build here, the velocity and the speed are the change in displacement, change in position over time. Acceleration is the change in velocity over time. So if an object is speeding up or slowing down, it's accelerating. Now, the one thing that we have to remember, though, is that velocity is a vector. And so there are actually 3 scenarios in which we can say an object is accelerating. If the speed's increasing, if the speed is decreasing, or, because velocity is a vector, if the direction of movement is changing, the object is accelerating. So if you have the car in cruise cruise control, so you maintain a constant speed, but you're turning a corner. Since the direction is changing, you're actually accelerating. Now our acceleration because our acceleration is change in velocity over time, it's meters over seconds, or meters per second squared. Now, if we're going to write this in IB notation, and this should be something you're comfortable with from math, meters over seconds squared is equivalent to meters per seconds to the negative 2. Okay, so this just means that it's 1 over that. Now within our acceleration equations, we're going to have a number of variables that are described or prescribed by IB, and you'll see them slightly different in different situations, but for us at this point, our distance and really our displacement also is going to be symbolized with a small s. It's measured in meters. Our initial velocity is going to be described with a lowercase u, and it's measured in meters per second. Our final velocity is measured in meters per second, and we symbolize it with a lowercase v. Our acceleration is a lowercase a, and it's meters per second squared, and then time is our lowercase t, which we symbolize with an s. These are the 5 variables that are going to be important in any kinematic situation, and really we're going to be using these variables throughout the entire year, not just in kinematics. And when we put these variables together in a couple equations, we get the 5 key acceleration equations. And here you see 4 of them, but in reality all of these equations come from or are derived in some form from the equation that is the definition of acceleration, and that is that acceleration is equal to the change in velocity over change in time. That's the definition of acceleration, change in velocity over change in time. And if we rearrange this a little bit, if we do a little deriving, if we say that acceleration, if we expand this delta v, we get vf minus vi over t. If we multiply both sides of the equation by t, we get at equals vf minus vi, and if we add the initial velocity to both sides, we end up with our final velocity equals our initial velocity plus at. Now this equation right here is this here, v equals u plus at. We also have displacement equals initial velocity plus final velocity divided by 2 times time, and all this really is the u plus v over t, or u plus v over 2 assumes a uniform acceleration, and actually all of these assume uniform acceleration. So let's clarify that. Uniform acceleration equations. The initial velocity plus the final velocity divided by 2 in uniform acceleration gives us the average velocity. And so this little square component here is the average velocity, so the total displacement is equal to the average velocity times time. And then our 2 equations on the right are a little bit more detailed, but we have displacement, s equals ut, so this is initial velocity times time, plus 1/2 at squared. And so this is the displacement that would occur if the object was traveling at a constant velocity, and then what we're doing here is factoring in the either additional or shorter displacement that's caused by the acceleration. So if you have a positive acceleration, that displacement is going to increase. If you have a negative acceleration, what you see this expression here is going to be negative, so it's going to travel a shorter distance than if it was traveling in a constant velocity. And then our final equation is final velocity squared equals initial velocity squared plus 2as. So 2 times acceleration times the displacement. And so with these 5 equations, 1, 2, 3, 4, and 5, we can solve any kinematics equation that we're presented with. Now for a little bit further in-depth analysis of where these come from, the derivation of each of these equations, you can see the related video called Derivation of Kinematics Equations.